Thanks to the organizers for having me here. Yeah, so I'll talk about part of my PhD thesis. And it should be clear from the talk that the paper of Rayer and Eugene on singular symplectic reduction has been an important source of inspiration for me. So yeah, I'd like to take the opportunity to thank them for that. Right, on to the math. So throughout the talk, G will be a compact Lie group, and I'll consider Hamiltonian G spaces with equivariant momentum map, which I denote by J. And I'll be mainly interested in the transverse moment map, which is the map induced by J between the orbit space of the G action on S and that of the co-adjoint G action. So one motivation for this is that I would like to get a better understanding of the symplectic reduced spaces. More specifically, what happens to these when we say change or vary the co-adjoint orbit O through the dual of the Lie algebra. And so the reason to study the transverse momentum map for this is that the symplectic reduced spaces are the fibers of the transverse moment map. All right, so the concise version of the main theorem that I would like to present to you, which is in this direction, is that there is a natural constant rank stratification of the transverse moment map. So roughly speaking, this means that there's a natural decomposition of this map into smooth maps of constant rank. This gives us insight into how both the singularities of the orbit spaces and those of the map vary throughout S mod G. All right. But before I say anything more about stratifications of maps, let me recall a bit about stratifications of spaces. So yeah, stratification of a space X is a topological space, is a locally finite partition into smooth manifolds, which are assumed to be locally closed subspaces of X. Usually, people also assume something more like the frontier condition on how the strata fit together, but for this talk, it's enough to have this in mind. Right, so there are various sources of examples of such of singular spaces that admit natural stratifications, such as algebraic varieties, or more importantly for us, orbit spaces of G actions on smooth manifolds. G is still compact. So the orbit space of every smooth G space admits the so-called orbit type stratification, as was also explained by Jordan yesterday. So the strata of these are connected components of the orbit type subspaces of M mod G. So these are the members of a partition of the orbit space defined by, collecting all orbits which are of the same type, where by being of the same type, I mean that they are isomorphic as G spaces. So this is equivalent to what Jordan explained yesterday. All right, so back to Hamiltonian G spaces. So sort of the starting observation that will lead to the main theorem is that, by the previous slide, both the domain and the codomain of the transverse moment map have a canonical stratification by orbit types, but the transverse momentum map does not have to be a map of stratified spaces. So even though it's equivariant, it can happen that there's a stratum on the left that is not mapped into a stratum on the right. So that's sort of the starting observation. And so starting from this, sort of the simplest way, if you want to fix this, the least thing you have to do is refine the stratification of S mod G. And the main theorem tells you that, there is a natural way to do so, so as to make the transverse moment map a map of stratified spaces. So there is a natural refinement, which I call the Hamiltonian stratification. This is a stratification and a refinement of the orbit type stratification on S mod G that does make the transverse moment map a map of stratified spaces, which means that it maps every stratum on the left into a stratum on the right, and when restricted to any two such strata, it's a smooth map, right? But there's actually more, which I mentioned before. The restriction of the map to any two such strata is of constant rank. So it has very mild singularities. All right. So a bit about the construction. So the construction is really analogous to that of the orbit type stratification, but now we consider something that I call J-orbit types. So these are defined in a similar way by defining a partition of S mod G, but now we don't just take into account the orbits in S, but also the coadjoint orbits down below in the dual of the Lie algebra. So note here that by equivariance, the moment map, it restricts for every orbit in S to a map into an orbit in the coadjoint orbit. And so we can define this equivalence relation saying that two orbits in S are equivalent if two restrictions are isomorphic as maps of G spaces. So this defines a partition, and the connected components of these members, they give you a stratification. Let me mention here that when G is abelian, the coadjoint orbits down below, they are points. So we just get back the orbit type stratification that we had before. But when G is non-abelian, already looking at simple examples of free action shows you that you really get something new. All right. So in the second part of the talk, I would like to say a bit about the Poisson geometry of the orbit space and how the Hamiltonian stratification fits into this picture. And this also relates to the symplectic reduced spaces. So for this, first let me recall some known things. For this, we'll only consider the moment map S mod G and the orbit type stratification on S mod G. So the first fact to recall is that the orbit space is so-called Poisson differentiable space, or so I don't really want to be precise about what I mean by differentiable space, but it's very similar to this notion of Sikorsky space, a structure. But morally, it just means that S mod G, it has a good notion of smooth functions, which are G invariant smooth functions on S. And there is a Poisson bracket on this algebra of smooth functions. It's just the reduced Poisson bracket, which comes from the fact, the simple fact that algebra of G invariant smooth functions is a Poisson subalgebra of that of smooth functions on S, equipped with a Poisson bracket of the symplectic form. Right, so this Poisson bracket, it's algebraic, but geometrically, this is reflected by the fact that the strata of the orbit type stratification, they actually are Poisson manifolds. And these Poisson structures that they have, they are determined by the Poisson bracket in the same way that a Poisson submanifold of an honest smooth Poisson manifold inherits a Poisson bracket. This you can express purely in terms of the smooth functions. And this is further related to the reduced spaces. So, of course, the symplectic reduced spaces are symplectic stratified spaces, as was shown by Eugene and Reyer. And they also showed that the symplectic leaves of S mod G, which is a partition of, by which I mean a partition of S mod G into symplectic manifolds, obtained by taking all the symplectic leaves of the orbit type strata. That partition is the same partition as the one you obtain if you look at all the strata of the symplectic reduced spaces and you vary the coadjoint orbit O through all the coadjoint orbits. Yeah, that's right. So the symplectic strata, they are contained in these level sets. Oh, do you mean level set? Yes. Well, in the reduced space, yeah. So the level set of the transverse moment map, yes. And well, in the paper of Reyer and Eugene, this is done expressed in a slightly different way. They don't really mention, I think, the full orbit type strata, but they use flows induced on the orbit space. But it's the same thing. All right. So yeah, as I said, now it's natural to wonder, how does the Hamiltonian stratification fit into this picture? And the answer, one answer, is the following. So they are again Poisson submanifolds of the orbit space. So they have an induced Poisson structure, but they're a little bit more special because they're regular Poisson manifolds, meaning that the dimension of the symplectic leaves on each such stratum is constant. And they're saturated in the sense that every symplectic leaf on a stratum is a symplectic leaf of the orbit space in the sense of the previous slide. So this really means that the Hamiltonian stratification, it groups the symplectic strata in such a way that they form regular Poisson manifolds. And secondly, these symplectic leaves are related to the fibers of the transverse moment map when you restrict it to the stratum. So the symplectic leaves, they form a regular foliation of such a stratum, but so do the fibers of the transverse moment map because it has constant rank when restricted to this stratum. The statement is that the two foliations agree. All right. Yeah, maybe so to end with some last properties, or some other properties. So the strata are not just regular Poisson manifolds, but they're actually of compact type, which means that they have a proper symplectic groupoid integrating them. And you can really build this proper symplectic groupoid in a natural way from the Hamiltonian G space. So it actually also carries information about the moment map and the action. There is a so-called, well, there is, for group actions, there is the usual principal orbit type theorem, which was also mentioned yesterday by Jordan, which says that if M mod G, the orbit space, is connected, then there is a dense open stratum in the orbit type stratification. So there is a version of this for the principal or for the Hamiltonian stratification, saying that if S mod G, the orbit space of the G action on the symplectic manifold, is connected, and the group is connected, then there is a dense open stratum. So there is a dense open stratum here, in that case. That also, so this is necessarily unique. And that also means that there is a distinguished stratum there. That actually has already appeared in the literature, which is the so-called principal wall of the Hamiltonian G space. So the dense open stratum here is mapped into the principal wall. So you can also use this fact to sort of reprove the existence of the principal wall. Okay, so finally, yeah, I have not said a lot about regularity conditions, but just in case you know, the Hamiltonian stratification, it's a Whitney B regular stratification. So it has really good properties for, well, amongst all stratifications. Yeah, and there are more properties, but this is all I wanted to say now. So thank you.